Okay, guys and gals, welcome to your very first flipped lesson in Algebra 2. We are in Lesson 1.1, Real Numbers and Operations. And I just want to remind you that this is coming straight from your book, so you can look at your book as we go along. This is on page 4. I want to talk to you first about numbers and how they relate in algebra. The most important set of numbers we use in algebra are real numbers, and I've drawn this out for you so you'll need to copy it and remember it. Real numbers are divided into two different types. There's rational numbers and there are irrational numbers, and let me take just a quick moment to explain to you the difference. Let me find a color here I want to use. So if you take a look over here at rational numbers, notice that this word ratio is right here. Rational numbers can be written in the form of a ratio. And if you know, ratios are fractions, right? 2 out of 3, 5 out of 10. So to help you remember this, if a number can be written in the form of a fraction, it is a rational number. If not, it's an irrational number. So when we move over to rational numbers, there's lots of different types of rational numbers. There are integers, whole numbers, and natural numbers. So we're just going to start with the basic, the natural numbers. When you think of natural numbers, those are, I'm sorry, I didn't mean to scroll up on you. Those are numbers that we naturally start with when we're counting. Numbers such as 1, 2, 3, 4, okay, and so forth. That's the easiest way to think about it. Whole numbers, there's only one difference between natural numbers and whole numbers, and the only difference is that whole numbers includes 0. So we've got 0, 1, 2, 3, 4, and so forth, okay? Now if we move on up to integers, I want you to think of a number line, and we know that we have negative numbers on the number line. Integers include those negative numbers. I did not mean to move that again. So if I included some of those, it would be -3, -2, -1, 0, 1, 2, 3, and so forth. Okay? Now, if I move on up to rational numbers, which all of these are rational numbers, by the way, but if they're not a natural number and they're not a whole number and they're not an integer, they're simply just a rational number. That means they're going to look more like a decimal or a fraction that can't be reduced any further, or a decimal if it repeats, because repeated decimals can be turned into fractions. All right, so I'm going to put just a few examples. Let me get my blue color right here. A few examples of rational numbers would maybe be 0.25, because that it ends right there. It can be turned into a fraction. If I gave you, let's say, what if I gave you, here's a really good one. Negative the square root, whoops, no, let me take that back. Let me take that back just a second. If I gave you maybe something 20, I am so sorry about that. I told you I was going to have to learn how to work this mouse. It's not a mouse, it's a pen, and it always messes up on me. I will get there eventually if you just bear with me, please. Now, let's go back. If I said maybe the fraction 22 divided by 7, that's as far as it will go. or even repeated decimals. Like I said, repeated decimals. Let's say 0.2713, and that 13 is repeated over and over. It gets caught in that pattern. They are rational numbers because they can be put in the form of a fraction. And all of y'all know, like the example we did the other day with Jake and his data, he used 2/3 of the data, and we noticed that was a repeated decimal, 0.66666666. So yes, it can be put in the form of a fraction. Now, irrational numbers are numbers that cannot be put in the form of a fraction and don't have any repeats. Probably the most common, I'm going to use a different color over here to show the irrational numbers. So probably the most common irrational number you can think of would be pi, 3.14, because it just goes on and it never ever repeats. Anytime you have the square root of a number that is not a perfect square, it is going to be an irrational number, because when you get this in the form of a decimal, there is no repeating and it just goes on and on. It doesn't stop like over here with 0.25. So hopefully this little graph here, chart, whatever you want to call it, will help you understand the difference between the real numbers, between rational numbers and irrational numbers. Alright, if you take a look on the middle of page 5, it gives you a definition of absolute value. We're going to need to know this in order to add and subtract real numbers. So the absolute value, all that means is the distance it is from 0 on a number line. Okay, so if you take 4, and I ask, and this here is the symbol for absolute value, and I ask you for the absolute value of that, well, the absolute value of 4 is 4 because it's 4 units from 0 on the number line. If I give you a -7 and ask you for the absolute value of it, well, it's a 7 because it is, even though it's negative, it's still 7 units from 0 on the number line. So we're going to need to know this in order to add and subtract real numbers. All right, when you add real numbers that have like signs, we're going to add the absolute values of those, and the sum is going to have the same sign as the add-ins. So for instance, if you have -5 plus a -9, we're going to add the absolute values. Absolute value of -5 is 5. Absolute value of -9 is 9. So 5 plus 9 is 14. But the sum, the answer, is going to have the same sign as the add-ins, and that's going to be negative. So your answer will be -14. Here's another example. If you have 23 plus -11, all right, we're going to add the where the signs are different. Sorry, the signs are the same here. When you have different signs, like this one, a positive and a negative, you're going to subtract the absolute values. And so let's do that first. We're going to subtract the absolute value. So the absolute value of 23 is 23. The absolute value of of a -11 is 11. And when we subtract that, we get 12. But the sum is going to have the same sign as the add-in that's bigger. So 23 is bigger than 11, is a greater absolute value, than 11. So that's why it's going to be positive. All right, we're going to move on quickly now to subtracting real numbers. Now, in order to subtract real numbers, we need to understand the property of an additive inverse. the additive inverse is merely the opposite of a number with respect to 0 on a number line. So if I said the number 2 has an additive inverse of -2 because they're completely opposite of each other in relation to 0 on the number line. -5 has an additive inverse of 5 because they're opposite of each other in relation to 0 on the number line. And to find the additive inverse quickly, you just simply change its sign. Okay, so the additive inverse of, hang on just a second, I'm playing with my pen again. Thing drives me nuts. The additive inverse of 3, the additive inverse is -3. Very simply, just change its sign. And because subtraction is defined in terms of addition, subtraction and addition are inverse operations. Alright, and we need to know that the additive inverse because we're working with real numbers, and real numbers aren't just 1, 2, 3, and 4. They have negatives. There's all kinds of fun stuff in there with real numbers. So we need to understand this in order to subtract correctly. So the definition of that is to subtract, we can add the inverse. Alright, that's what we're going to do. This is on page 7. The number subtracted, the number that you're taking away, is called the subtrahend. To subtract, we can change the sign of the subtrahend, what we're taking away, and then add it to the other number. So let's take a look at a couple examples and then we'll be finished. If I have 5, take away -4, what I'm going to do is add the inverse of the subtrahend. -4 is the subtrahend. So if I'm going to add it, I'm going to say 5 plus, and the inverse of -4 is 4. So 5 plus 4 is 9. Hopefully that makes sense. So we'll do one more and show you it like in a fraction. -4 thirds, take away -2 fifths. Alright, so that would be -4 thirds, and I'm going to add the inverse of the subtrahend, and the inverse is +2 fifths. Alright, and so we can't do that. We need to find a common denominator, which would be 15. 3 times 5 is 15, so 4 times 5 is 20. And I'm going to make that common denominator 15. 5 times 3 is 15, so 3 times 2 is 6. So that would equal 26 over 15. Oh, look what I did. Did you see my mistake? It's supposed to be negative. See what little bitty mistakes can happen. It's -4 thirds. Sorry about that. Negative. So I'm going to get my eraser pulled up right here. Thank goodness for erasers. And I'll take this answer away. And we'll go back. Now we can do that. So this will now be -14 over 15. See, even teachers make mistakes too. All right, we'll do some of these in class. Thank you very much.